We present high-resolution neural face swapping for visual effects, an unsupervised deep learning method for generating high-definition, multi-way, photorealistic transfers of source appearances to target actors. Our method produces compelling and convincing results that are difficult to distinguish from genuine images. In our pipeline, we begin with data for the behavior we want to model. We perform face alignment by detecting facial landmarks. We transform and normalize the face to 1024 by 1024 resolution. We then feed it into our model and decode it as any one of the source appearances our model is trained for. We then blend the generated face with the target background using a contrast-preserving, multi-band compositing process. The method encodes multiple faces in a shared latent space via its common encoder and decodes images using multiple decoders specialized for individual faces. This has the effect of disentangling static identity information from dynamic behavioral information. This makes any performance transferable between any two identities in our data. Facial landmark labeling can be unstable from frame to frame when working in high resolution, so we introduce a routine to correct for these errors. The effect of the correction is subtle but noticeable. Notice in the clip on the right the quivering of the mouth and the slight rotation of the face below the eyebrows. Those artifacts are not visible in the clip on the left. Our model supports a progressive training regime that allows us to generate high-definition video at a resolution and level of realism far beyond competing methods. This training process also allows us to avoid a number of artifacts that occur if the model is trained end-to-end at full resolution. To achieve convincing full-face swaps, we apply a contrast-preserving multi-band compositing process, which achieves nearly seamless blending of generated images with target backgrounds while maintaining the color and lighting characteristics of the target image. Our multi-way model not only allows any pair of identities in our data to be swapped, but also provides for richer representations of facial behavior. Here we compare a source-target swap using our model trained on only 2 identities, with the same swap in a model trained on 8 identities. Notice that the 8-way model more faithfully reproduces the target behavior, despite both models seeing exactly the same data for the specific source-target pair. We compare our method with several open-source implementations by applying the source identities at the bottom to the target performance at the center left. The original deepfakes method takes on a gauzy appearance, while the stylized autoencoder from Deepface Lab has noticeable difficulty producing a convincing blend. The 3D morphable model approach of Nirkin et al. Suffers from pronounced temporal instability, although individual frames can often look reasonable. By contrast, our method leads to clean, high-detail results with no apparent seams or artifacts. Our model allows for a broad range of dynamic information to be represented in the latent space. When we interpolate along the learned manifold, the resulting decoded images correspond to realistic and coherent behaviors that define a clear continuum between their boundary points. Importantly, our method does not simply index existing data, as these nearest neighbor results illustrate.